roll number 2, Aurobindo Parai. Roll number 3, Purushottam.
Yes, sir.
Roll number 9, Mausam Raj. Roll 11, Priyabrata Nashko.
Present, sir. Present, sir.
Okay. Roll number 14, Nawaz Rahman. Roll number 15, Vinay Kumar. Roll 17, Shagni Kojar.
Yes, sir.
Roll number 19, Supriya Barai. Roll number 23, Paulami Roy.
Present, sir.
Roll number 24, Shubham Kumar.
Yes, sir.
Roll number 25, Saurabh Das. 26, Vikas Biplab. Roll number 30, Megha Shankar.
Present, sir.
Roll number 31, Shiv Mahato.
Yes, sir.
Shiv Mahato. Raju Kumar. Roll number 32. Roll number 35, Jitendra Kumar. Roll number 36, Sauman Sen. Roll number 38, Chandan Kumar. Roll 41, Jasimul Haq. Roll 42, Aniruddha Shah. Roll 43, Isha Paja.
Yes, sir.
Roll 44, Mayank Raj. Roll 45, Samanita Banerjee.
Yes, sir.
Roll 46, Samay Ghosh.
Yes, sir.
Roll 52, Abhishek Kumar.
Present, sir.
55, Mukesh Kumar Chaudhary. 58, Dipanesh Das. 63, Subhashri Datta.
Present, sir.
70, Deepak Bhatt. 71, Debarshi Shah.
Yes, sir.
72, Madhuvan. 'Anyone left in the attendance? Okay. So, after a long gap, we will be commencing our lectures on PMOS and NMOS circuits. There will be a rebrushing as well as we'll move on further. Let me share the screen. Is the screen visible? Is it visible? Yes. Is it visible or not?
Visible, sir.
Okay, so today our topic is NMOS and PMOS circuits. And before we proceed into the circuit design phases, we will try to redraw the symbolic representation. So the symbols of PMOS and NMOS, which were the arrow-based symbols, are replaced for the sake of simplicity to a more digital pattern. So the PMOS transistor symbol will be with a bubble at the gate terminal, and the NMOS transistor circle will be without any transistor circuit, will be without any bubble in the gate terminal. So this is what a PMOS is, and this is the PMOS. This is the NMOS symbol which we will be using in our further circuit. So we already had an idea about the PMOS NAND, NOT, NOR and NAND gate. So again, let us redraw using this symbolic representation. The biasing potential is negative, minus VDD. The load transistor is gate terminal is connected with the drain. From the driver transistor, we provide the input. There must be a bubble over there. In between, we take the out. Here we provide DG. This is the PMOS NOT gate. NOT gate. And for the PMOS NOR gate, the load transistor remains the same. And the driver transistor has to this is the PMOS NOR gate. PMOS 2 input NOR gate. Similarly, we can draw the PMOS 2 input NAND gate. So again, the load transistor remains the same. Driver transistor, there are two driver transistors, or in other words, the driver network comprises of two PMOS transistors cascaded. This is the PMOS 2 input NAND gate. So one thing we can see that whatever be the logic you design the driver network or the driver transistor, the output is just the reverse. So for 2 input NOR gate, you OR 2 PMOS transistor at the driver network, you make it in an OR fashion, and you receive a inverse of that OR logic, that is NOR. Similarly, for the PMOS NAND gate, you AND 2 PMOS transistors, you connect that in a cascaded way, and you receive at the output the NAND logic. So that's the inverse. So any logic you represent within the driver network just gets inverted at the output. So following this logic, if you are provided with a Boolean expression, say you are being provided with a particular Boolean expression, Z equals to A plus AB plus A bar B bar. So this kind of an expression in an inverted form. So what is this expression all about? So this is the inverted expression. Within the inverted bar, you have the expression AB plus A bar B bar. If you consider both A and A bar as two separate Boolean variables, then you can draw the PMOS circuit in a much simpler fashion. So what will be the PMOS circuit for this expression? The PMOS load transistor remains the same. It is connected with the biasing power supply, which is minus VDD. And the driver network you will be realizing with the expression below the inversion bar. So AB plus A bar B bar. So how it will look like? So there is a plus, that means there is a parallel branching, and within each parallel branching there must be cascading of two transistors each. So if this is A, sorry, there must be a bubble. This is B. We have A bar, and the input is B bar. Connect these because these are in parallel branches. Ground it from an intermediate point between the driver and the load to collect the output. So Z will always be the inverse of the logic which is being represented within this driver network. So this is nothing but the driver network. This is the driver network. So what is the logic being represented? The logic represented within the driver network is AB, because both these A input and B input transistors are cascaded. Then it is in parallel with again both A bar and B bar inputted transistors cascaded. So as it is in parallel, you use plus, and then as again it is cascaded, A bar and B bar input transistors. And what I have mentioned, that for this kind of PMOS circuit, the output will just be the inverse of the driver network. So this is nothing but. So you have realized Z, which was made to realize by you. Now, if you can simplify this Z. If you want to get a simplified form, that what is Z, you will get A bar plus B bar A plus B. So if you use De Morgan's theorem and break this expression in a simplified form, it will be like this. Now say you have a question that this portion is not given to you. So if this portion is not given to you, only you have this logic being provided, Z equals to, say, Z equals to A bar plus B bar into A plus B. Then this is a expression without any inversion bar. You have to convert this expression into this form for designing the PMOS network, because any driver network you design must be inverted at the output. So you need an inverted expression first, and then the expression which comes below the inversion bar must be realized within the driver network, so that when you get the output at Z, you get the inverted form of AB plus A bar B bar, which ultimately resembles A bar plus B bar into A plus B. Am I clear, students? So if you are having a non-inverted expression such as Z equals to, say, the XOR logic AB bar plus A bar B, and you are asked to design a PMOS circuit, you need first to convert this into an inverted expression. This is a non-inverted expression. It doesn't have a whole bar over it. So you need to convert that into a inverted expression. How to convert that? So double bar means no bar plus. So this lower bar, just break this, use De Morgan, then what it becomes? AB bar, whole bar, and this sign will change. A bar B, whole double bar. Again, further reduction. So again, you can break this line and change the sign below. That is what De Morgan says. A bar plus B double bar. This into remains. Here, A double bar plus B bar. So ultimately, it simplifies to A bar plus B, A plus B bar. Is it clear? Did you understand what I have done?
Yes, sir. Clear.
Okay, fine. Now you have got an expression below a single inversion bar. So now this non-inverted expression, this non-inverted expression is converted into an inverted expression or into an inverted form, which is this one. So now you can design your PMOS circuit. So Z equals to ultimately Z becomes this. So how to design the PMOS circuit? The load transistor remains the same. It is connected with the biasing power supply, which is minus VDD. And for the driver network, we do not term it as driver transistor because there will be multiple number of transistors taking inputs of these Boolean variables. Here, there are two sub-expressions in a cascade form. And within each sub-expression, there will be parallel branching because there is flux. So ultimately, what is it? First expression, V bar plus B. Then it is cascaded with another expression or small expression called A plus B bar. So you cascade that and create another two parallel branching into A and B bar. Okay, then you ground it. And from this is the driver network which we have designed, and the load transistor remains same. So in between a point between the driver network and load transistor, you take your output as well. So did you get it? How to design PMOS circuit?
Yes, sir.
So we had a non-inverted expression, which is basically a two-input XOR gate. This is a two-input XOR gate, A B bar plus A bar B, that is being converted into an inverted form, and we do get an inverted form by using De Morgan's theorem. So here, using De Morgan's theorem of Boolean algebra, we use it and convert it into an inverted form, A bar plus B to A plus B bar. And the expression below this inversion bar is realized within the driver network. So this is nothing but the driver network. And obviously this is the load transistor. So The design criteria is for PMOS circuit, load transistors, gate terminal with drain which is connected with the biasing potential, which is minus dB. Second, the driver network comprises with PMOS transistors connected in a pattern of expression simplified in an inverted form. And if you have the expression already been given in an inverted form, you do not need this simplification. So this simplification using De Morgan theorem is not needed if you have already a inverted expression. If you do not have an inverted expression, then you need to simplify this expression in an inverted form, and then you connect the PMOS transistors in that pattern. Is it clear?
Yes, sir.
Now, if you can design an inverter circuit, a NOR gate, as well as a NAND gate using PMOS transistors, you can design any digital circuit using PMOS transistors, because NOR and NAND are universal logic gates. So any digital logic can be realized using PMOS transistors. Now, whenever you are provided with a Boolean expression, you need to understand that whether it is in an inverted form or in a non-inverted form. If it is in an inverted form, then already half job is done for you. You need to realize the expression below the inversion bar within the driver network, and the load transistor remains the same. In from an intermediate node between the driver network and the load transistor, you derive your output. If the expression is given in a non-inverted form, you need to convert that into an inverted form using De Morgan's theorem, as I have done. And the expression now below the inversion bar needs to be realized within the driver network. This is how any PMOS circuit can be designed. So there should not be any problem. Let us now concentrate towards the NMOS circuit. So first, the NMOS inverter. What the significant change is, it is within the load transistor. Rest of the thing remains the same. Obviously, these transistors are NMOS transistors, but here the load transistor is such a NMOS transistor whose gate terminal is connected to source, not connected to drain, and the biasing potential is positive. plus VDD. Here the gate terminal is connected to source, not connected to drain, mind it. And this transistor, NMOS transistor, is slightly a different type of NMOS transistor. It is a diffuse channel NMOS transistor, signified by this. So this is the load transistor. To be precise, it is diffused N channel load transistor. So diffused N channel load transistor is symbolized by this pattern. The channel is shaded. The channel must be shaded for symbolic representation of diffused N channel load transistor. If the load transistor would have been induced N channel, then it would have been without any shade. This is induced N channel. Induced N channel. MOS. For diffused N channel MOS, you must shade this portion. This is diffused N channel MOS. So what is the difference between induced N channel MOS and diffused N channel MOS? For diffused N channel MOS, so obviously N channel MOS means the substrate will be of P type. How it looks like. This is the SiO2 oxide. This is the metal or the gate, and we have N class regions over here, and this is P-type silicon. Now, for diffused N-channel MOS transistor, even when you have the gate to source, so this is the gate to source, maybe the drain to source. So VGS is a constant potential. This is VGS, which is a variable potential. So for diffused N-channel MOS transistor, already electrons are diffused within the channel, few amount of electrons. So even if VGS is 0 volt, you haven't provided any potential at VGS. Even if VGS is 0 volt, we get a substantial value of ID or drain current. We do have a substantial value of ID when VDS is constant. So when VDS is constant, we have a substantial value of the drain current even when VDS is 0. So even when VGS is less than the threshold potential, VGS is 0 means VGS is less than VTH, because for NMOS transistors, this VTH is typically plus 0.7 volt. NMOS transistors made of silicon, this VTH is typically plus 0.7 volt. So VGS is 0 voltage, VGS is less than VTH, less than the threshold voltage. So even if VGS is less than threshold voltage and no electrostatic induction takes place within the channel, no electric field is created, even in that situation, you have a substantial value of the drain current or ID as you provide a drain to source potential. This is the characteristics of a diffused N-channel MOSFET. So here for NMOS circuit, we use a diffused N-channel MOSFET as the load transistor. And then we have the driver network, and the driver network is designed just similar to how we have designed the PMOS circuit. So what will be the NMOS inverter. So the NMOS inverter will look like something like this. The load transistor is a diffused N-channel load transistor. Biasing potential is positive. As per the driver transistor, here for the inverter you have only a single driver transistor. So this is input. There is ground from an intermediate point. You take the output. Or in other words, this is D, this is D out. So this is nothing but the NMOS inverter. So what is the main difference between the PMOS inverter and NMOS inverter? Of course, the transistors here are NMOS transistors, not PMOS transistors. But the significant difference is the NMOS load transistor will be a diffused N-channel NMOS load transistor where the gate and the source terminals are shorted. The gate and the source terminals are shorted. In other words, G and S are shorted means VGS is 0. Here G and S is shorted. That means the value of VGS is 0. So diffused N-channel load transistor also works typically if you provide the drain to source potential. And as you have connected the drain with VDD and the source with 0 volt without any potential connected, so you have a positive drain to source potential which will trigger current flow or the drain current flow through the channel even when VGS is 0 volt. So this is the NMOS inverter, and similarly we can draw or design the NMOS NAND and NOR gate. So for the NMOS 2-input NOR gate, so this is NMOS 2-input NOR gate, and for NMOS 2-input NAND gate, we have a cascaded kind of a thing. Positive biasing potential, very important. You should not miss this as positive. This must be positive biasing potential. And you have two cascaded NMOS transistors connected with one another. V1, V2, ground the last transistor, take a output from my intermediate node, V out. So NMOS 2-input NAND gate. So similarly, for any kind of Boolean expressions, you must be able to draw the NMOS network. The only difference between the PMOS network is here you are using NMOS transistors in place of PMOS transistors. The load transistor, very important, is here a diffused N-channel load transistor. So its symbolic representation also changes, and the gate terminal is connected shorted with the source, not with the drain. So it is lower bound shorted, and then the biasing potential you connect with the drain terminal of the load transistor is a positive biasing potential plus V. So this is the difference. So let us try to redraw the circuits which we have already drawn for PMOS transistors. So let us have the 2-input XOR gate. Z equals to AB bar plus A bar B. So this is nothing but 2 input XOR. So the same design criteria here again, as because this is in a non-inverted form, you have to convert that into an inverted form. Convert that into an inverted form. So I am just omitting the steps over here. You should not omit the steps because otherwise there may be error. A bar plus B into A plus B bar. This is the simplified logic of the XOR gate. And here to design the NMOS, let us design it in the next step. So A plus B into A bar plus B into A plus B bar below the inversion bar. So we do have the load transistor drawn first. It is a diffuse channel load transistor connected with the positive biasing potential. The gate terminal of this load transistor is shorted with the source, and then you start designing the driver network. Here it will comprise of 2 cascaded branches. Within that, there are parallel transistors connected. So A bar and B. Then it is grounded. Do not forget in any of the circuit you design, do not forget lastly to connect the output terminal from a in-between point between the load transistor, this is diffuse N-channel load, and this is the driver network. Is it clear, students?
सर एक बार आगे स्लाइड पे जाओ सर और जस्ट आगे
Yes.
स्लाइड पे सर ये
Pardon?
आगे स्लाइड पे
Here, Abid. This one.
हाँ हाँ
Is it clear?
Yes.
So anyone up to this, any confusion? So the design of PMOS and NMOS circuits are quite similar. In terms of your driver network, you have to use the logic, Boolean logic to design the driver network, and that logic is same for designing the PMOS circuit as well as the NMOS circuit. Now the differences are for PMOS circuits you use only PMOS transistors, for NMOS circuits you use only NMOS transistors, and the load transistor is the major difference between these two circuits. For a PMOS transistor, the load transistor is the conventional one, where the gate terminal is connected with the drain terminal, whereas for the NMOS circuit, the load transistor is a diffused N-channel load transistor, whose gate terminal is connected with the source terminal. The biasing potential's polarity is also different. For PMOS transistor, it is minus VDD. For NMOS transistor, it is plus VDD. So whether it will be plus or minus depends on what is the threshold potential for PMOS and NMOS transistor. For PMOS transistors, the threshold potential is minus 0.7 volt for silicon made transistor. For NMOS transistor, it is plus 0.7 volt for silicon made transistor. So, as because the threshold potential is positive for NMOS transistor, you use the positive biasing potential. As because the threshold potential is negative for PMOS transistor, you use the negative biasing potential. Rest of the circuit design patterns are quite similar. So, for any Boolean expression, if you are able to design a PMOS circuit, similarly, you may be able to design a NMOS circuit also. Is it clear? Any confusion? Yes, students? Okay, so I will be stopping the lecture for today up to this, and tomorrow again I will be having another lecture from 9 o'clock, 9 a.m. morning. Is it clear, Isha?
Yes, sir.
Tomorrow again another lecture from 9 a.m.
Okay, sir.
Most of the days we will be conducting lecture classes in extra with that of our scheduled routine, because there will be certain gaps in this month of November where I will be not taking any lecture class. That I will be intimating you afterwards. But for this week and the coming week, we will be having most of the days we will be having lecture class. Okay, is it clear?
Yes, sir.
Thank you, everyone.
Thank you, sir.